Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering. Previously we discussed Young's modulus of elasticity, which is the stress strain relationship related to length, okay, change in length of the material, longitudinal stress or tensile stress, and longitudinal strain, tensile strain. In this video we are going to discuss about bulk modulus of elasticity. Okay, so here we know that stress, which is basically the reaction to the externally applied deforming force, the reaction force. So when we talk of stress, it is basically the reaction of the material to the externally applied force. It is equal and opposite, obeying Newton's third law, which is to every action there is an equal and opposite reaction. So that internal reaction force acting per unit area, that is called as stress. Okay, so applied force by area, always remember that. I am reviewing this so that you are clear of what we are discussing. So this stress can be of different types. It can be related to length, change of length, which is basically these two. These are longitudinal stress, that is tensile and compressional. Then we have bulk or volume stress, which is acting uniformly on all sides. This is related to volume. And this is the sliding stress, which causes bending of materials. So this is related to bending angle. So here we'll discuss the bulk or volume stress. So if you remember, bulk stress is the stress which is basically uniform. It acts on all surfaces of the body, and the reaction force in response to those externally applied force, that is called as the bulk stress. So this is basically bulk stress. Example of that is the hydrostatic stress when a body is subjected in water. So the strain which is resulted in response to bulk stress, strain is basically change in dimension to the original dimension. Now this dimension, it can be length, volume or bending angle. Here it is volume. This dimension is volume or change in volume. So bulk strain or volumetric strain is basically change in volume to the original volume. Let's say we have an original volume of V of an object. In response to the bulk stress, it either increased in volume or decreased in volume. Here we are talking about decrease in volume. Okay, we are talking about this part. Increase in volume we are not discussing here. We are discussing only about this. Okay, let's say because of hydrostatic stress, the volume shrinks, decreases by a margin of minus delta V. So here the volumetric strain, it will be delta V by V, and there will be a negative sign also here which denotes decrease in volume to the original volume. The negative sign will be there. So volumetric strain is minus delta V by V. Now here we'll apply Hooke's law to bulk modulus of elasticity, which establishes a relationship between volumetric strain and volumetric stress, bulk strain and bulk stress. So basically Hooke's law states that within elastic limit, stress is directly proportional to strain. That is, the strain produced in the material is directly proportional to the applied stress. So here for volumetric analysis, volumetric stress is directly proportional to volumetric strain. That is, the change in volume per unit original volume is directly proportional to the applied volumetric stress. So here it is sigma subscript V is directly proportional to epsilon subscript V. This is volumetric stress and this is volumetric strain. Okay, so here let's say we have an original object of certain volume V, and because of the applied volumetric stress, there is a reduction in the volume. Okay, there is a reduction in the volume by this margin. So the volumetric stress and the area, the cross-sectional area of each face is A for simpler analysis. So here the volumetric stress is force by area, force acting per unit area, and the volumetric strain is change in volume or decrease in volume by original volume. Again, a negative sign will be there. Okay, decrease in volume by the original volume. So here, according to Hooke's law, the relationship is volumetric stress is directly proportional to volumetric strain. Sigma V is directly proportional to epsilon V. So here, the proportionality constant, which is the ratio of volumetric stress to volumetric strain, that gives us the bulk modulus of elasticity. That is, sigma V by epsilon V is the bulk modulus. And this bulk modulus is expressed as this. Okay, F by A, which is the volumetric stress, and delta V by V, which is the volumetric strain. And the negative sign, it indicates that there is a reduction in volume as compared to the original volume. So we can write it as this bulk modulus of elasticity is equal to minus Fv by A delta V. We went to the numerator and A came to the denominator. Okay, this is the formula for bulk modulus of elasticity. Okay, so now here there are some important things. Again, here delta V by V, both of these, they have the same units, volume units, so they will cancel out each other. Force by area, force is Newton, area is meter square, so it will also have the unit of Newton per meter square, same as Young's modulus. Same thing, they will all have the same units. Young's modulus of elasticity is also Newton per meter square. Bulk modulus of elasticity is also Newton per meter square. Again, as I said, the negative sign, it indicates a decrease in volume with stress increase. As the stress is increased, volume decreases. Okay, and bulk modulus of elasticity has unique values for different materials. Okay, it has different values and is always specified in the specification sheet when you purchase a particular material for any purpose. Okay, any application purpose. You have to take into account the bulk modulus of elasticity before putting it into use for specific use. Now, it is unique for a material and it depends on the nature of the material, the physical, chemical nature, everything, it comes into play. Now, there is another important parameter which is compressibility. So, if we take the reciprocal of bulk modulus of elasticity, if we take the reciprocal, then what we get is the compressibility. Okay, 1 by bulk modulus of elasticity, that gives us compressibility. The compressibility of a material. Okay, so this is the concept of compressibility, which is the reciprocal of bulk modulus of elasticity. Now here are some bulk modulus values for some commonly used materials. Again, it is expressed in terms of 10 to the power 9 Newton per meter square. So whatever the value it is, that into 10 to the power 9 Newton per meter square. So for aluminium it is 72, copper 140, iron 100, water 2.2, glycerine 4.76, mercury 25, ethanol 0.9. Now again, these are values. Now they are not specifically accurate. It's not that 72 means 72. There will be some plus minus, some margin of error, but these are rough estimates. Okay, rough approximate values. So these are some commonly used materials with bulk modulus values. There are other materials also, you can check their values and compare it with these values. So these are bulk modulus of elasticity constants for commonly used materials. So here we have discussed the bulk modulus of elasticity, which establishes a relationship between bulk stress or volumetric stress and volumetric strain. Okay, so here the relationship between the volumetric stress and volumetric strain, that gives us the ratio, the constant gives us bulk modulus of elasticity, and it has this formula. Okay, so these are some commonly used values. So here we have discussed about. Okay.